Okay, so the outline of my talk is the following. So I will present double color spectroscopy. So why do we study this? Of course, because we can. But the idea is to get some new information of a chemical shift, and I will give you some hints on this. And how to do this? So we have two options, which are two-photon absorption with X-FEL lasers. So we have heard a lot of this during this conference. But I will present here, it will be rather single-photon double ionization using synchrotron radiation. I will after present the experimental setup, which consists in detecting in coincidence all the photoelectrons and the Auger electrons which are emitted in this process, and that led to the spectroscopy of double color states and to the selective Auger decay. And I will show you experimental results, and the experimental results, I will speak of single-site double cohorts, K-2, but also double-site double cohort states, which correspond to the ionization of two K-shell electrons on two different atoms. And after I will present the Auger decay of these states, and I will end with some related process which corresponds to ionization and excitation of core electrons. So the story starts about 30 years ago by a prophetic article by Lance Sederbaum, who made some calculation on the C2H2, C2H4, and C2H6. And okay, so at this time it was completely impossible to do this kind of spectroscopy, but he had the idea to do this calculation, and he says that if you ionize two electrons on two different atoms, instead of having something which chemical shift which is rather small if you do single ionization on carbon atoms in this series of molecules, you will have a strong chemical shift in this series due to the different bond length and due to different effects that I will explain later. Okay, so but 25 years after, this topic came to the forefront because X-ray ferroelectron laser will arrive. And also Lance Sederbaum with Robin Santra made this publication speaking of X-ray two-photon photoelectron spectroscopy. In this case, they take the parabenophenol molecule with the very different molecules. And if you absorb two photons on different sites, you will have a very rich electron spectra that will give you some information on the localization of the atoms in a molecule. So the first experimental results came immediately after, first on 3-electron lasers. So you have seen, I think, this picture in some previous talk. And so here it was on 3-electron laser, it was the first observation of double K-shell ionization by the observation of a hypersatellite Auger electron in nitrogen. But almost at the same time, our group and also the group of Raymond Feifel with John Eland, who was participating to the two experiments, observed double K-shell ionization on a single atom in different molecules, CH4 and ammoniac, and also for us on N2, CO, CO2, and O2. Okay, I will come later to this. 1 year after, we had the first observation of double K-shell ionization on different atoms in a molecule. So with X-ray free-electron lasers, the game is rather difficult because you have to play with the focusing of a laser to remove a single photoionization, and with this, playing with this different focusing, you can show the multiphoton effects, and you have here a signature of two-side double cohort production that correspond to K-1, K-1 in CO molecule, and you have also K-2 ionization that corresponds to double ionization of a carbon K-shell. So with synchrotron, it arrives with us so we did measurements at photon factories, I will detail a little bit before, and this was the first evidence of double K-shell ionization of the two carbon atoms in the acetylene molecule. So I should also mention that very recently that was an attempt. So on X-FEL you have so many photons that it's almost impossible to do coincidence experiments because you ionize everything, and also the repetition rate is not high enough to do properly coincidence. So the other way is to do covariance mapping, and there was this publication by the Raymond Feifel and Frasinski, who was specialists in this covariance technique, and they observed also some signature of double K-shell ionization using this specific experimental method. I will not go in details on this. Okay, so the experiment we are using is based on synchrotron radiation. So we did experiments on the Soleil synchrotron in Saclay on different beam lines. And these are the people who participate to the experiments. Here is our group with experimentalists and theoreticians in Paris. And we had also collaboration with Slovenia, Finland, Johnny Land from Oxford, and Kenji Ito also from Photon Factory. And at the same time, up to the end of 2011, where we had still single bunch at Photon Factory, we did the experiment at Photon Factory with all these people here. Okay, so I will show you now how the experimental setup is working. So basically, it's most of you probably know how a magnetic bottle time-of-flight spectrometer is working. So you have a small permanent magnet that creates a strong inhomogeneous magnetic field that collects all the electrons and parallelizes the trajectories in a few centimeters. And after, you have a long solenoid that guides the electron toward the detector after a 2-meter time of flight. So the properties of this spectrometer is that you collect all the electrons from 0 up to 900 eV with an efficiency that is almost 4 pi solid angle up to 200 eV. And the detection efficiency, due to the channel place efficiency, goes from 70% for up to 200 eV and decreases slowly to the highest energy. So the resolution with a 2-meter-long spectrometer is typically 1.5%, which is good enough for low-energy electron and still acceptable for Auger electrons, for instance. And with this very high efficiency, you are able to detect in coincidence 2, 3, 4, and up to 5 electrons if 3 electrons are produced in the same multiple ionization event. I should mention also that when you have more than 2 electrons, 3 electrons, we lose the angular information, but when you have more than 3 electrons, it's hopeless to keep all the angular information on 3 electrons. But of course, what you need, and what is now not so easy to get, is you need single bunch to have this time-of-flight measurements on synchrotron. So this means 2 weeks a year, for instance, in Soleil. Okay, so I have here a very schematic image of double ionization. So I start by single-site double cache ionization in acetylene. So you have 1 photon coming in and ejecting 2 photoelectrons. And after this, you will have a first Auger decay by emission of a high-energy Auger electron, which is called hypersatellite Auger electron, which has an energy something like 50 eV more energetic than the normal single cache Auger electrons that are here. You have all the process at the same time. And in a second step, you fill the second cache hole with the emission of a second Auger electron in this energy range. So in this case, you have 2 photoelectrons that share the available photon energy. And you have 2 Auger electrons that have different energy so that you can detect all these electrons in coincidence. And this is what we did here, indeed. So I present results for nitrogen because it was the first experiment we did at Photon Factory, and after we did experiment on acetylene. So they are isoelectronic. So the only difference is that we accumulate more counts in the acetylene than nitrogen, but the spectra are very similar. So here it corresponds to a 4-fold coincidence. So we have 2 electrons, 2 photoelectrons and 2 Auger electrons. And here I plot the energy correlation between the 2 photoelectrons, knowing that at the same time we have detected 2 Auger electrons. So you have lines here that correspond to constant sum of the 2 photoelectrons, and that give you the energy of a state you are producing. So this is the energy correlation. So we have different lines here that corresponds to double Cauchy ionization with simultaneous excitation of another valence electron. So now I look specifically on acetylene. So if you look at the first state here, which corresponds to double Cauchy ionization on 1 carbon atom, you have 2 photoelectrons emitted. So the energy sharing between the 2 photoelectrons gives this typical U shape here, which is characteristic of direct double ionization, like what you have in helium. So, but now I have to speak of efficiency of this process. And what we measure, because with the magnetic bottle we have all the efficiencies for all energy of the electrons, the typical probability to have double Cauchy ionization on a single site in 1 carbon atom in this acetylene molecule is typically 10 to minus 3. So this means you have to wait some time to get a good signal with good statistics. So doing this, you have just to add up the energy of the two photoelectrons, and after with this relation, you have a binding energy of the final states, and this is the spectra you get for nitrogen and for acetylene here. And this is the calculation that were done a few years ago by Stefan Carniato to reproduce our results. So the ground state is where we produce. The agreement with the excited states is more difficult to obtain, but we have at least the good shape for these energies. Okay, now I move to the other process. How can a single photon ionize two electrons from two different atoms? So you can imagine it will be more difficult with a single photon to eject two electrons from two different atoms separated by more than 1 angstrom. And one other difficulty in this case is that even if you create this process, we will have a first Auger electron here that will have almost the same energy as the second one. So this means, due to the dead time of our detector, it will not be possible to detect two of the Auger electrons. So this is what we did with detection of 4 electrons, 2 electrons, 2 Auger, 4 coincidences, in order to show this double Cashel ionization on 2 different sites. So we have to look now at 2 electrons in coincidence with 1 Auger. So when you reduce the number of coincidences, of course, you increase the random coincidence level. So this explains why the background increases. But something appears, so you are probably not convinced. There is a very thin line here. And believe me, when you project this, you get this peak. And this peak is exactly where we expect the signature or two-side double ionization. So, and the agreement with the theory is good in this case. So this was the first observation of this process. So to get this data, we had to accumulate typically during 12 hours with 20,000 counts per second. So we have gigabytes of data, and at the end, we have a few thousand counts on this peak. So now the probability also to have this process relatively to single Cashel ionization. So the ratio of K-2 single side double Cashel ionization to single ionization is, as I said before, 10 to minus 3. The ratio of double Cashel ionization on 2 sides with respect to double Cashel ionization on 1 side is typically 2%. So this means the double Cashel ionization on 2 atoms on the acetylene molecule is something in the range of 10 to minus 5. So this is a very small signal, but due to the coincidence, we can extract this line very clearly. So if you want to have a very rough estimation of this process, you have just to consider some billiard game. And if you consider the ratio of a solid angle, so if you start with 1 photoelectron here, the solid angle to hit the second electron on the same atom is 2 pi. And the probability to hit the second electron on the neighbor atom here is 2, because you have 2 electrons taken by the solid angle on which you see the 1s orbital from the other center. And if you do this, you find 1.4%. So it's just the order of magnitude. So this means that the most probable process is just knockout of the other electron by the first photoelectron, which is some internal collision in the molecule. So after this, you have Auger decay. So when you select these states here, here, and here, so this is the normal Auger decay from the single Cashel. This is the Auger spectra from single side double Cashel. And this is the Auger decay from the 2 sides where we have only this peak. So the high energy part here is the hypersatellite. So I will go in more details because since we have also all the coincidence, we can play the same game. So we select the 2 photoelectrons. So we select the ground state, K-2 ground state. And we have now the coincidence between the 2 Auger electrons. And this is how it compares with theory that was developed by Tashiro. So here we have the hypersatellite, which fits very well. But we have in the second step, we have some broadening of experimental spectra compared to the calculation. This is probably due to the fragmentation before Auger decay of a triply or quadruply charged molecule. So for the second peak here, which corresponds to double Cauchy ionization and simultaneous excitation of a valence electron, we have also the same spectra, and these peaks here that give this wing on the high energy side correspond to participator Auger decay. So all this is possible due to the efficiency of our experimental setup. So to summarize the results we get on all these molecules, here for K-2 we have, in the first paper by Cederbaum, you don't expect a strong chemical shift for K-2. But what was not predicted in this prophetic paper is that even if you don't have a strong shift, you have a strong difference due to the valence electrons which are excited in the process. And if you consider the similarities between all the isoelectronic molecules here, C2H2, CO, and N2, you have a very similar spectra between this, and this. So for K-1, K-1, we continue the experiment on the C2H2N series, on CO and also on N2, and there was this clear signature. And in this case, we have a typical energy shift of 3 eV between acetylene and ethylene, and of 3 more eV between ethylene and ethane. And this is mostly due to the Coulomb repulsion between the two Cauchy holes, which depend on the bond length here, plus relaxation effects. So in the case of CO, it's much easier because you have one Auger decay on the carbon and one Auger decay on the oxygen with different energy, and you can have 4 electron coincidences. So for nitrogen, it was more difficult because we have less photon at this energy than at lower energy. But finally, we could see this. And what is also interesting is that the ratio of a K-1 process follows the solid angle dependence with the bond length of here. So here is a table that summarizes the results we obtained, and we have something which agrees qualitatively with the prediction of Cederbaum 30 years ago, but was greatly improved by Tashiro in the recent years. Okay, so but this was for simple molecules. So the idea was to extend it to bigger molecules. So can we do this? So the basic molecule that was used for chemical analysis was the SIGBAD molecule, the ethylfluoroacetate, where you have 4 different carbon atoms with very different environment. So in this case, you have these well-isolated photoelectron peaks. So, but when you do this for K-2, you have this coincident spectra. And in the middle of the spectra, you have a single Cauchy ionization of the fluorine atoms. And this induces strong random coincidences. So if you want to reduce the random coincidence, you have to reduce the count rate. But if you want to see something corresponding to the K-2 in this case, you have to count much longer time. So at one moment, we are at the limits of what can be done. So it was possible to observe this. So we have a stronger chemical shift for K-2 compared to K-1. But the statistics remains low. And for this, we accumulate more than 12 hours. OK, so these are my conclusions on double coral states. So we have studied K-2, K-1, K-1. We have seen the spectroscopy. We have observed their decay by cascade Auger emission. So we can study the intermediate and final state. And now I move to the last topic of my talk, which is simultaneous coionization, core excitation that I summarized by K-2V. So this can be seen as precursors of double coral states, but you can also think of this as super K-1 shakeup, or also aborted K-2 ionization. So in this case, you have one photon that ejects one photoelectron, but since you have 2 core holes that are created, you will have 2 Auger electrons. So but you have 2 ways to arrive to this process. You can say, OK, so I absorb the photon and ionize first, and after I have some shakeup, direct shakeup. But I can also excite one valence electron, and simultaneously, I can have shake-off of another electron. So you can summarize this by these 2 matrix elements. But the interest, when you are close to the double ionization threshold, these 2 processes have almost the same probability. And this is much different for conjugate checkup when you have only valence electrons. So the results are there. So this corresponds to free electron coincidences, where I plot the correlation between the photoelectron here and the hypersatellite Auger electron. And at the same time, we have detected a third Auger electron, which corresponds to the last cascade decay. So here we have different processes. I will not insist on this. So you have core valence ionization and you have Auger decay. And the process we are interested in is exactly this. So we have the photoelectron and in coincidence with the Auger electron here. And here it's just double Cache ionization where you miss one of the photoelectrons. It's just the sum scars of this process. So the result we get for this, also on this C2H2N series, we got the following spectra. So, and in this spectra, we have different processes. And if you look carefully, you have one big peak here for acetylene, which is divided by 2 for ethylene, and which is completely absent for ethane. And this, for people who know the Nexa spectra on the same molecules, this corresponds to excitation of a pi resonance. So this is absent for ethane. And so, in fact, at a fixed photon energy, you have at the same time some signature of direct checkup states and also of conjugate checkup with similar intensities. So we continue the game. So moving to CO2. So this is at the carbon Kh. So this is carbon K-2 ionization. So this is, and if you look at the same states, K- excitation and ionization of a Cache electron on the carbon atom, you find 3 peaks. So the first one in green here corresponds to the pi resonance. It corresponds to conjugate checkup. So the red one corresponds to direct checkup with a sigma resonance. And the third peak is a composite of different processes where you have direct and conjugate processes. So in this case, the ratio of the first peak to the second peak is about 2 to 1. So the idea was for us was to see if we can really see some variation with photon energy of this ratio. So we asked our colleagues on the Galaxy beamline. So it's the team of Marc Simon with Tatiana, all these people, and Maria Novella will give some details probably in the next talk on the Galaxy beamline of the spectroscopy you can do. So at 2,300 eV, you expect a signature of this K-2 process around 1,000 in this region. But the problem is you have mostly the K-1 line from oxygen. So if you increase a little bit, you have all the satellites of oxygen. And you have really to accumulate much longer time, about 1,000 more counts, to see very small peaks here. And with this, you can subtract some background, and you found 3 peaks. So this is as a function of the electron energy. And these 3 peaks, you convert this in binding energy. This is the difference between the results I presented just before at 760 eV, and now at 2,300 eV. In this case, the ratio that was of a factor of 2 at the lower energy now is moved to a factor of 1/3. So the interpretation for a moment of these results is in progress. Okay, so now I conclude on this process. So this, in fact, to study this process, if you are in a good situation, you have only to detect the photoelectron if it is somewhere in a space where there is nothing else. So what is interesting is to see how the evolution of these two processes, the direct checkup and conjugate checkup with photon energy. We have also studied the variation of peak widths for different molecules. So we were able to see vibration in N2 and also dissociation in H2O. And my general conclusions are here. So with multi-coincidence spectroscopy, we were able to reveal this double Cauchy ionization very clearly. So the energy sharing corresponds, in fact, in direct double ionization of the K orbital. So, and with these coincidences, we are able now to detect processes which are in the range of 10 to minus 3 for K-2, and also to 10 to minus 5 for K-1, K-1. So this can be obtained in some reasonable accumulation time. And this process can be very interesting and the message I want to give is really you want to observe double cache ionization. Ideally, we would need X-ray free electron laser with much more repetition rate and less than one molecule to be able to do coincidences. Okay, so thank you for your attention and thank you for staying here.